Welcome, everyone. Thanks for joining us today for today's science session, a deep dive into elevated temperature landfills. I have a couple of housekeeping items to go over before we begin. So you can submit questions anytime throughout the presentation using the Q&A icon at the bottom of your screen. And then in terms of a certificate of attendance for the presentation, tomorrow you will receive an email from Zoom with a link to both the presentation and a survey. And there you can also download your certificate of attendance if you need those for any sort of continuing education credits. Thanks for joining us today. I'm Susie Boxman. I'm the Director of Programs at the Environmental Research and Education Foundation, where I oversee and manage all of the research that we do and fund at the foundation. But I'm really excited to welcome today's speaker, Dr. Morton Barlaz, who is a distinguished university professor emeritus at the Department of Civil Construction and Environmental Engineering at North Carolina State University. He's been involved in research on various aspects of solid waste since 1983, including biological refuse decomposition, methane production, the fate of hazardous waste in landfills, policies for the long-term management of landfills, and factors contributing to heat generation and accumulation in landfills. He is also recognized for his research on the use of life cycle analysis to evaluate emissions associated with alternative solid waste management strategies. So join me in welcoming Dr. Barlaz, and I'm going to turn it over to him for today's science session.
Okay, great. Thank you, Susie, and thanks everybody for joining. Really excited to have the opportunity to give this presentation. And as Susie said, we're going to talk about elevated temperature landfills and try to focus on monitoring applied research and best practices. This outline came from the seminar announcement, so you've already seen it, but we'll try to define ETLFs, talk about what we've learned from research over the years, indicators, best practices, and where I think we're headed. So let's begin, and I hesitate to call this a definition. Different people like to call things, say things differently. But in generally, an elevated temperature landfill, or ETLF, is a landfill where we're seeing heat accumulation over a broad area. So the key here, I think, is that if you just have two hot gas wells and they're above 130 degrees Fahrenheit, that's not an elevated temperature landfill. But where we see temperatures above, say, 160 degrees and the heat appears to be spreading across multiple wells, that's probably heading towards what meets the criteria for an elevated temperature landfill. There are a limited number. I don't have a precise count, but there's a handful. But we have seen several with temperatures above 100 degrees. And suffice to say, these landfills require a lot of attention. This is just some sample data, and I'm gonna talk about various indicators. The first indicator being temperature. And temperature could be temperature of the gas, temperature of the solids from a borehole, or temperature of liquids in a gas well or possibly leachate. Typical temperatures, if we're below 65 C, and I'm not seeing an increasing trend, I'm okay, because methane generation is going to proceed with minimal inhibition, if any. And here's some data where we see a normal landfill with temperatures as high as 50 or 55 C. But here's an elevated temperature landfill. Notice that the heat is accumulated maybe 2/3 of the way down, not near the top. It cools quite a bit at the bottom, but we've got temperatures as high as 130, 140, 145 degrees C. So clearly, this is an elevated temperature situation. So the easiest indicator is temperature, whether it's the gas, the solids, or the liquids. A second indicator is gas composition. Indicators would include a decreased methane content and an increased content of carbon dioxide. There could also be a possible increase in carbon monoxide and hydrogen, but I'm going to stress throughout this presentation, I don't want anybody to hang their hat on one indicator, except perhaps temperature. Because, for example, carbon monoxide, well, it can be produced biologically. Hydrogen is produced biologically. It's also quickly consumed, and because its molecular weight is so low, it moves quickly. So I like to see multiple indicators, not just one. The one that we use the most is we look at the ratio of methane to carbon dioxide and look for a decreasing trend. And I'll also note, not an indicator, but if you've got low methane content, the gas may not burn well in a flare or engine, which may result in a discharge of incomplete combusted organics, which could contribute to odor. Now, on the right side of this slide, you see gas well temperatures. In this case, they were increasing. Before we understood much about ETLFs, the site shut the gas well off, the exact wrong thing to do. When they turned it back on, the temperature shot way up. And similarly, the methane to CO2 ratio shot way down. This is atypical. Here's more typical. Here is a decreasing trend in methane to carbon dioxide ratio. And this is what you'd see if you're operating a well continuously. And I'll stress throughout this presentation the importance of plotting your data, looking at it, looking for trends. I say interpret gas well composition cautiously and just give an example where gas well composition might be misleading. So in this slide, the blue are cross sections where temperatures are normal. The red is a cross section where temperatures are hot. If the normal sections are producing gas at typical rates and the hot section is inhibited, you can see we might have 80 CFM of good gas generation and 5 CFM of weak gas generation. That's going to be diluted if I just take a sample that's an average of this entire well. So that's why I say interpret data cautiously and let's look for multiple indicators, not just one. Some other indicators, rapid settlement, extensive crack development, steam coming out of gas wells, or if you're drilling to put in new gas wells and steam is coming out of borings. If you're seeing damage to gas and leachate infrastructure, typical PVC pipe will melt or soften and bend. And if you're boring, again, very typically the hottest temperatures are deep in the landfill, not at the boundaries. And note that these deep landfills with low surface area will retain the most heat. And of course, water accumulation will exacerbate heat accumulation. Another indicator is leachate quantity and composition. Many sites that are ETLFs report increased leachate. And that begs the question of why are they getting leachate, increased leachate? And there's two possibilities. One is the solids have degraded. There's less solids to hold the water, and therefore the field capacity of the waste is decreased, which is going to release more water. And there may be reactions that produce water. But a characteristic of most ETLFs is they're saying elevated generation of leachate. And then leachate seeps. Leachate seeps, of course, they could just be inadequate cover, but they could also be perched water or perched water with gas pressure, pushing that water out the side. So these are indicators that make you want to look further. And certainly if you're seeing leachate seats and don't have temperature data, this would be a very good time to get it. Leachate composition. ETLFs were typically seeing elevated leachate strength. I mentioned COD, phenolic compounds, decreased pH. So here's an example where you can look at the time since the reaction started. So time zero is this zero. And below that, we see BODs of 100 or 100 or 500 to 500, CODs around 1,000. But then as that BOD to C, as that reaction starts, we see a huge increase in the BOD and the COD to between 50 and 100,000. And a lot of that is biodegradable as measured by the ratio of BOD to COD. As with the gas, consider where that leachate sample is coming from. Is it a gas well liquid where the leachate might be concentrated? Or is it a header over 50 acres where maybe only 5 acres or 10 acres are hot, where it might be diluted? So I think the message here is if all you're doing is collecting over a very, very wide area and you don't see an indicator in the leachate, that doesn't mean you don't have an ETLF because it might be diluted. So again, we want to look for multiple indicators. So to kind of summarize early indicators, decreasing methane to CO2, presence of carbon monoxide, elevated organics and low pH in the gas, leachate seeps. Lagging indicators, things that happen later, elevated gas and liquid temperature, unusual settlement, deteriorating leachate quality over a wide area. And then I put this comment, not attributable to concentrated food waste. If you've ever had, say, an acid stuck situation where there was very concentrated food waste, the fermentation exceeded methanogenesis, that led to an accumulation of carboxylic acids and a low pH. In a shallow area, that could be a low to concentrated food waste, probably less likely to occur at depth. Now, notice that these indicators are different from fires. I don't list melted gas wells. I don't talk about localized settlement. And I can't emphasize strongly enough that ETLFs are not fires and they should not be managed as fires. And as I've said, look for multiple indicators, not just one. So what does this lead to? Well, challenges. Odors due to fugitive emissions, possible incomplete combustion. The settlement could lead to site instability or damaged infrastructure. I mentioned leachate and gas pipe softening. And of course, if the elevated temperature reaches a geomembrane, then it's got the potential to damage that geomembrane. I think most sites I've seen, the temperature has cooled before it hits the geomembrane. Increased leachate strength, and suffice it to say, there are going to be operational challenges. If there are odors, there are going to be community challenges and regulatory attention. So lots of challenges if you've got a site that is exhibiting elevated temperature, or lots of potential challenges. Some pictures. Left is a leachate seep. The middle is waste that had essentially pyrolyzed. And the right is pressure relief from drilling a borehole and seeing some steam shoot up because there was water under pressure. So let's transition and talk some about causes. There's been a lot of research, as I'm going to describe. I'm going to emphasize the fact that we are not always sure what causes an ETLF, and the after-fact focus needs to be on management and control. 100% proof of the cause may not always be possible, and frankly, what's important is to manage it. Lots of speculation. I try to stick to the facts. Reactive waste can explain temperature elevation at some sites, but others are largely municipal solid waste. So let's talk about some potential causes or some reactions we know about that generate heat. One is ash. Ash undergoes both a hydration reaction, shown here as CaO plus water going to calcium hydroxide, and then a carbonation reaction where that calcium hydroxide reacts with carbon dioxide, which is plentiful in landfills, and makes calcium carbonate. And of course, that calcium carbonate will be in the solid phase, and I'm sure some of you have experienced clogging of leachate lines due to calcium carbonate. Just to stress here, CO2 is a gas. Carbonic acid, bicarbonate, and carbonate ions are dissolved. Those are all forms of carbon dioxide. They all react. Landfills essentially have an infinite supply of carbon dioxide. Another reaction is aluminum, and we've seen this manifested with both aluminum dross and baghouse fines, but we also have landfills that accepted dross that did not exhibit elevated temperatures. If you have an aluminum waste and it's mixed with an alkaline waste like ash or some other off-spec waste, Under alkaline conditions, aluminum corrosion is accelerated to a great degree. Look here, aluminum is giving off over 10 times as much energy as iron during corrosion, so we worry a lot more about aluminum than iron. I'll talk more about what about the aluminum in foil or cans or aluminum sheet. And I'll talk more about that when I talk about research, but the anaerobic environment um, uh, basically prevents this protective coating from forming. But if we're looking at ash, the combustion will burn off that protective coating. And we'll come back to aluminum from municipal solid waste in a few minutes. There is an abiotic cellulose, so landfills are, paper, yard waste, food waste, all has cellulose. Landfills are on the order of 30 to 50% cellulose. It's probably closer to 30 now because we're using a lot less paper than we did 20 years ago. That cellulose can undergo an abiotic hydrolysis reaction and give off heat. Now, how significant is that? I'm going to talk about that when we get to research findings. And then non-reactive waste. So the cellulose, the aluminum, the ash are reactive. Perched water will impede gas collection and promote heat accumulation. And this can be particularly problematic in a landfill with a high surface area to volume ratio, such as a quarry. And these are results from a modeling exercise, and we'll talk more about this in a few minutes. But just looking at the, say on the right, the volume fraction that exceeded about, I think it was 45 degrees in the 40-meter high landfill and the 80-meter high landfill. And here we see it again, the solid lines are the 80-meter landfill over 6, 15, and 30 years. It's hotter than the 40-meter landfill simply because it's higher and we are reducing heat loss. Another and maybe I shouldn't call air a non-reactive waste. I don't think of air as reactive, but actually it does undergo a biological reaction, so it is reactive. Air intrusion, likely only a potential issue at the surface, not at depth. If you see a site with high nitrogen and little to no oxygen, it could indicate air intrusion and then facultative microorganisms consuming the oxygen. But there have been some field reports of very high nitrogen with no air intrusion, which would suggest nitrogen production. And I'll be the first to say I'm scratching my head over this. The traditional way to make N2 gas would be from nitrate, but we just don't see that much nitrate. So to me, this might be the next research project. Of course, if I see high N2 and O2, that suggests air intrusion above the waste. But in general, I've not seen air intrusion to be a factor at ETLFs. It tends to be a factor at the surface, not in deep sites, especially deep wet sites. Thank Craig Benson for this slide, just kind of summarizing what I've said. But here's the water table. And if I've got water and I've got heat generation down here, that heat is going to be slow to dissipate. And that can certainly exacerbate heat accumulation. So summary on causation. Landfills are complicated, lots of confounding factors. They're hard to simulate in the lab. So causation, some, none, or all of the above factors may be the cause. A general observation that goes beyond landfills is that industrial accidents seem to result from multiple things going wrong at the same time. So reactive waste plus liquid accumulation plus heat release. Now I've got 3 things going wrong as opposed to any just one. And so again, there's complexity, and I want to emphasize the need to manage as opposed to focus forever on causes. I'm going to present now some highlights from research, and I always like to start with this slide because it's based on Some of the work is based on modeling, some is based on experimental work. George Box is a very famous statistician, and I love the quote, all models are wrong, but some are useful. And the point is, we're not going to write a model of a landfill and predict the temperature within 2 degrees. But if we can write a model of a landfill and predict which way things are moving, that helps us. And here's exhibit number 1. When we started what's really probably an 8 to 10 year research program with EREF, the first thing we did is write a fairly simple model. We included various reactive waste, and the conclusion was, hey, both ash and aluminum contribute a lot of heat. This black dotted line is MSW, the green line is ash, and the purple line is aluminum, and say, hey, these are important. Now, all the inputs for these models were based on the literature outside of landfills. But that said, okay, our priority needs to be to study ash and aluminum. We used that very simple model and we made a lookup table that said, okay, how much calcium do you have in your ash? 15, 20, or 25%. How much of that calcium is calcium oxide versus calcium hydroxide? How much of the calcium hydroxide has already been hydrated, and so on. And we get a lookup table. So just as an example, at 20% ash, if I've got a 15% calcium in that ash, and it all comes in as calcium oxide, the model says you're going to get 191 degrees F. Now, I'm sure you're not going to get exactly 191 degrees F, but it tells you, hey, that's too hot. I need to back off. On the other hand, if I get 10%, it's only 161 degrees. So we generated a lookup table, which was a first set of guidance on waste acceptance. Now, at the end of this, I'm going to show you how every ash is unique and we need measurements. Let's talk about aluminum corrosion again. Within municipal solid waste, we see aluminum in the form of foil, cans, and sheet. We did some work in the lab. And the good news is corrosion was not measurable at 60 degrees C. And that suggests that corrosion is not, or corrosion from the aluminum in MSW is not initiating an ETLF. If, however, a landfill were to reach 70 degrees C, then aluminum corrosion would exacerbate heat generation. To complicate things, we used 3 different field leachates and got 3 different results. We showed foil followed by sheets and cans in terms of corrosion rate. Well, what are the takeaway messages? Number 1, if you do have a large amount of aluminum, don't put it in a concentrated area without planning for potential heat and hydrogen. Do not mix aluminum with alkaline waste because that will accelerate reactions. And then an observation. A biological reaction shuts down when the temperature gets too hot. An abiotic reaction, like aluminum corrosion, is not self-regulating. It speeds up as the temperature gets hotter. So we may get a situation where we get to the upper end of biological heat generation, and that's just enough to start stimulating more heat generation from abiotic reactions, whether it's aluminum corrosion or abiotic cellulose hydrolysis. And then, of course, if I got a deep, wet landfill with poor heat removal, I'm exacerbating that situation. And I just noticed that we have an EREF report on this that was released earlier this year. Abiotic cellulose hydrolysis, I'm going to get to the same point. We did lab experiments in deionized water. With pure cellulose, we saw quite a bit of hydrolysis, which would result in heat release. Then we started to be more realistic. We used copy paper and newspaper, and we used leachate. And the leachate seemed to actually inhibit abiotic cellulose hydrolysis. But like aluminum, this is an abiotic reaction. It's going to speed up as the temperature increases. So do we get a situation where, again, the biology gets us to a point where the abiotic reactions start making more heat? Possibly. And again, alkaline waste will accelerate cellulose hydrolysis. Um, Another thing we learned, and I don't know that we learned this from research, but we certainly quantified it from research. If I've got an area of the landfill that's hot, and that hot gas moves laterally to a cool area and condenses. When it heats up, it sucks heat out of the waste. When it condenses, it releases heat. So I did a very simple thought experiment. Let's start with gas at 70 degrees centigrade. Um, and imagine that box A is 10 times bigger than box B. And the initial temperature of box B is 40 degrees. Um, After a year, box B is going to get to 60 degrees C in the worst case. So that's my 10-to-1 ratio. So this is just really a thought exercise, but to point that another mechanism for heat spreading is hot gas spreading laterally and condensing, which is another reason to be aggressive about extracting gas and not giving it the opportunity to migrate outside of the reaction area while it's hot, because then it's going to condense and you've got a mechanism for spreading. Um, Here's some more model simulations. 3D means three-dimensional finite element model. Just showing what happens if we put a column of ash in the center and allow both hydration and carbonation versus carbonation only. And so now I'm going to show you, hey, can we get the ash wet before we bury it and get rid of that heat of carbonation above ground? And then we've got less heat to deal with. This is a summary of a number of model simulations. CNLV, the cumulative normalized landfill volume. So let's look at the volume of the landfill above 65 and 80 degrees C for a number of scenarios. So ash in center, hydration. So I built a column of ash with hydration and carbonation, and I get 7% above 65. But if I wet it above ground and then I've got carbonation only, that goes to 3%. If I put it in the corner, I get slightly different numbers, although given the accuracy of the model, I don't know that they're significantly different. But what is important is look what happens when I mix the ash in with the MSW as opposed to segregating it. I heat up a lot more of the landfill. So the takeaway message is segregate ash. And that leads to these comments: place heat generating waste in locations where the heat can dissipate, either close to the surface or segregate it. Containers, maybe a monofill or a block fill, but don't mix it in with the MSW. So here's some field work where we had the idea of neutralizing combustor ash before burial. So we built piles, and at time zero, you see some calcium carbonate and some, I'm sorry, and some calcium oxide. Little calcium, calcium carbonate, calcium hydroxide. So this is day zero, 3 different sample locations. Then we go to day 35, 55, and 87. Now let's skip over here. I've consumed all of the calcium hydroxide and I've made calcium carbonate. And the total calcium is roughly the same as the calcium carbonate. So the point is, I was able above ground to let that ash react with carbon dioxide in the atmosphere, carbonate, and now I've basically let that react above ground. When I put it in the landfill, there's no more heat generation potential. And my final slide on ash, again, this is an EREF project. And this is a very busy slide, but I'll walk you through it. Again, the results were published in an EREF report earlier this year. But what you've got here, C1 through 6 are coal ash samples, M1 through 6 are MSW ash samples. The blue bar is the heat of hydration. The gray bar is the heat of carbonation. Message number 1 is look at how different these ashes are. Each ash is unique, and we can't predict it There was some work at Central Florida to try to predict heat release based on the elemental composition. We can't do it. Each ash is unique, and we need to test it. Now, using these heat shift hydration and carbonation, then we used our model to say, okay, what temperature do these give? This dotted line is MSW, just at about 60, 62 degrees. And you can see some of these were getting to 70, 80, in this case, 130 degrees C. So if I've got that ash, and this is 20% ash. So what's the message? If you have any confidence in the model, you don't want 20% of this ash in your landfill. Maybe you want 5% or 2%, or you're very, very careful to segregate it and let that react where it's not going to impact the MSW. We had the opportunity to get some samples from an elevated temperature landfills. These are my dedicated graduate students and postdocs. We sampled 2 landfills, and the depth is on the left column, and then you see the temperature of the waste as excavated. So take-home message. This is methane generation versus time. The sample was 75 C or 167 F when it was excavated. When you incubate that sample at 72, we didn't get any methane. So in other words, no acclimation of microbes to hot temperatures. But as I cooled it, it started methane very quickly. So at 167 F, we did not kill the methane generation or the methane producing microorganisms. We inhibited them, but as soon as we cooled it, they came back. And I saw a similar observation with some field data at the Congress landfill, which is on the north side of Chicago. Now, I don't know how high they went. I don't know what happened if this 167 is 250 instead. I suspect then we would not get as promising a result. But nobody's done that. Nobody's done that test. And maybe it would come back, but slower, because microorganisms will find micro niches and some may survive. Final comment, or not final comment, final slides on what did we learn from research. What you're seeing are field data from boreholes at a landfill experiencing, as you can see, temperatures up to 178 Fahrenheit. The dotted line is field data. The red line is our model. So is it a perfect fit? No. Is it a decent fit? I think it is. Made me feel pretty good about the model. And what I think is particularly significant is the hottest temperature in the model simulation was between temperature probes, and it was consistent with the location of ash disposal and gas well temperatures. And so while temperature probes are certainly important for monitoring the site and making sure you're not spreading or tracking spread, if the temperature probe doesn't go in the reactive waste, it might not show you the hottest temperature. So temperature probes are an indicator, but the limitation is they may or may not be in the hottest part of the waste. So wrapping up, what have we learned from experience? Maintain aggressive gas collection. Get the gas out. That reduces pressure. It pulls out a little bit of heat. ETLFs are not fires. Where there's a fire, the assumption is you've got an air intrusion problem. And with an air intrusion problem, yes, you want to shut down or lower the vacuum on your wells. ETLFs are not fires. Keep removing the gas that may require, from a regulatory perspective in HOV, they're just essential. The worst thing you could do would be to turn off the gas well. Look at your data. Look for troublesome trends in well temperature and gas composition data. Don't just collect the data. Look at it, plot it, look for trends. Keep the site draining. Do not allow perched water. Do not allow liquid to accumulate. Your gas collection system, we like to talk about well coverage, but gas collection is a combination of well coverage and cover quality. So install covers that work with the gas collection system to enhance collection and, of course, reduce infiltration. And then waste acceptance programs and develop test protocols. The protocol we use to measure heat release from ash is not what the commercial labs are using. And as far as I'm concerned, it's what they need to be doing. We can manage ETLFs. We can't turn it off in many cases. There might be sites where we can stop progression. There may be sites where it moves, but we need to aggressively remove heat. And when we're talking about sites that are 250 feet deep, the idea we're going to, sprinkle some magic or inject something magical to stop a reaction, I would not personally spend a lot of time thinking about it. I don't think we can do it. And might go all the way back 25 years. Everybody was excited about bioreactor landfills. We're putting water in landfills. Even then, we couldn't get all the waste wet. So why do we think we'd come in now to 200 feet deep and get all the waste neutralized in some way? Every site has unique conditions. So I've tried to speak a little bit in generalities, looking for multiple indicators, multiple lines of assessment, look for multiple lines of evidence. Every site is unique, and I think about the worst thing we could do is pontificate a one-size-fits-all approach, and it might work at a site or two, and it probably won't work at all sites, and it might do more harm than good at some sites. So I really feel strongly that every site is very unique. Future directions. Vigilance, I've already said, data review, not just data collection. Aggressive, rigorous, state-of-the-art operations for gas and leachate control, and waste acceptance. For ash, commercial labs need to be measuring heat generation from hydration and carbonation. Most of the data I've seen is hydration only, and they're missing a good chunk of the heat. The tests for each waste type are going to be unique, and they may have to be designed. So I think partnerships with labs are needed to develop the right test for each type of waste. There's not one generic test that's going to work. So just to conclude, I could not have given this presentation without working with a lot of people for well over a decade. There's been graduate students and postdocs. There's been other colleagues at NC State, as well as at Craig at Wisconsin, Marco Castaldi in New York, Scott Ludick, who's now retired from Geosyntec. There's been a lot of interaction with industrial colleagues, bouncing ideas, pushing each other on, well, you think that, but can you prove it? What do the data tell us? What don't the data tell us? And of course, financial support from both EREF and Waste Management. And I could not have given this presentation if we removed too many of these bullets, because everybody's input has just been invaluable. And then I'm not going to read all these, but we've got lots of papers in the literature, and you'll get the slides, I think Susie said, tomorrow. So these are available, and 2 of them are EREF reports. So they might be, depending on your access, the rest of these would have to be purchased because they're copyrighted. But with that, let me thank you and turn it back over to Susie to moderate questions. You're muted, Susie.
Yeah,
There you
and Zoom is great. It popped right up. I'm still muted.
No, we
There we
can hear you.
go. Okay, I'm good now. So thank you very much for that overview on ETLFs. We have quite a few questions coming in, and then we got a few questions that came in advance of the presentation. So I think one of the questions that we got in advance that I kind of wanted to cover, and I think you covered some of this in one of the last slides, about what we've learned from experience, but there were a couple of folks asking, how do we lower temperatures? So it sounds like maybe there are limited approaches to actually lowering temperatures, but I mean, is there any more that you can say if once you have an ETLF, what do you do?
Yeah, I think once you have it, I don't think over a very broad area you can lower temperatures other than remove as much heat as you can. And as you remove heat, you're also increasing the opportunity for the heat to dissipate. And the analogy I like to give is imagine you have a swimming pool and the water in the swimming pool is 150 degrees. Um, don't jump in. If you took half the water out of the swimming pool, the other half would still be 150 degrees. On the other hand, you will have lowered the ratio of, excuse me, you will have increased the ratio of the surface area to volume, so you will have enhanced heat dissipation. And so I think it's all about removing the heat you can, and in so doing, you are increasing heat dissipation. But I don't think you can go into a 50-foot thick waste column, cross section that might be 100 or 150 feet below grade and inject something and cool it. And in fact, I think I saw one site where they tried an injection and all it did is cause breakouts on the side slope. Didn't cool anything.
Mhm. Hmm. Do you have any information on how widespread this is as an issue? I mean, is this something that's worldwide? And do you know how much other countries might be dealing with this issue?
Well, I have a theory, but I don't have any proof. I can share that I did give a talk of this nature to the International Waste Working Group, which is primarily European and Asian members. And the Europeans listened, and they don't put a lot of biodegradable waste in landfills anymore, and really hadn't seen any reports. The Asians, I'm much more suspicious that there are some ETLFs, and my suspicion is because their waste is a much higher concentration of food waste, so their waste is a lot wetter. So remember what we talked about. Don't let water accumulate. Um, and my guess is that there are sites in Asia where there may be water accumulation. And the challenge is that they don't all collect gas. So if the methane to CO2 ratio were 0.1 or the gas temperature were 190 degrees, they wouldn't know it because they're not measuring it. So my suspicion is that there might be some of these in Asia, but I don't have any evidence. The other place I'm a little suspicious is Australia, just because, and I hate to generalize across a whole country. You can't generalize across the US, but you got maybe some deep quarry fills. On the other hand, it's pretty arid. So they may not have the water accumulation issues. I don't know, but I have not read of any documented ETLFs any place other than the US. That, however, may be, because nobody's looking.
Hmm. Interesting. So one of the questions we got in advance was also kind of asking about the effects of elevated temperatures on landfill liners, and whether or not you have any guidance or what the research is that on how the ETLFs impact liners.
In answering questions like that, I love to remind people I know a lot about most aspects of landfills other than the geotechnical. Um, so with that caveat, I think there's lots of data in lots of testing where people have shown that at some temperature you do reduce the effective life of a geomembrane liner. I don't know what that temperature is, but it is well documented in the literature. and it does reduce the effective life of the geomembrane. Now, that said, two caveats. One, I think all or most of the sites I've seen, the temperature is cooling before it gets to the liner.
Mhm.
So most ETLFs that I've seen data on, the hot temperature had not spread to the point where it would be hitting the liner. And then the second observation is we love to talk about liners, but we actually have in landfills are liner systems, right? We have leachate collection, a geomembrane, and then clay. So let's just stipulate that we do damage the geomembrane. First of all, we're damaging it over some fraction of the site, not the entire site. Second of all, we're still removing leachate. Um, so we don't have a huge, or we should be removing leachate. And so we don't have a huge hydraulic head. And third, we have clay, which is restrictive. So we don't want to damage geomembranes, but landfills were built with a liner system, not just one layer.
Mhm. Thanks for that. So, another question, any relationship between ETLFs and black slime or black goo? I know Dr. Benson has also done a lot of work on the black
Yeah.
goo issue, and for reference, EREF has a webinar or a science session on black goo that Dr. Benson provided. But Dr. Barlaz, do you have any thoughts on the relationship between those two?
Um, I was involved in the GWMS session on black goo, and the drivers for the black goo seem to be leachate flow under quiescent conditions, which is not related to ETLF conditions. And the second driver was waste composition that has nothing to do with an ETLF. It has to do with these little package of acrylates that are going into all kinds of products just to keep the humidity low before the consumer uses them. And I cringe now every time I open a bottle of vitamins or something, and there's this little packet in there that I really wish I had something to do with it besides put it in the landfill. So neither of those have anything to do with ETLFs. As recently as 2 weeks ago, I was at an ETLF and asked if they were having black goo problems, and the answer was no. So I don't know if Craig's on, and I don't know if he can speak or perhaps type into the chat, but I've not seen a relationship. But Craig would certainly have more. Dr. Benson would certainly have more firsthand knowledge than I do.
Absolutely. Um, so back to the leachate aspects of ETLFs, does the ETLF cause the increased leachate, or is their relationship, or is it the other way around? The increase in leachate causes a ETLF. Obviously, it's not obviously there are lots of things that
Okay.
cause ETLFs,
Yeah.
like you said, but what's the relationship
So
between leachate?
when you say the relationship between leachate, do you mean the relationship between leachate composition or quantity?
Quantity.
Quantity. Well, I think it's not so much the quantity as it is if that leachate doesn't drain. If it drains, if it drains to the bottom, that leachate collection system can remove it. And we don't have a situation where water is accumulating um, and reducing heat dissipation. Where the leachate quantity becomes a problem is, for example, I was visiting a site sometime in the last few years, and they had a road system, as all landfills do, and they felt that the road system had been very, very well compacted, which you would expect as you run trucks over it. And then it wasn't removed before they went on to fill more. So they, in essence, built, I don't know if it was clay or not, but they, in essence, built the clay liner in the middle of the landfill. And that resulted in perched water, and that resulted in heat accumulation. So I don't think the leachate is the cause. I think the way the leachate is managed and the attention to leachate management is a contributor to heat accumulation, which is what we're worried about. We don't want heat to accumulate.
Mhm. So circling back to the black goo issue, Craig did type in an answer, and he also hasn't seen a connection between black goo and ETLFs.
Thank you.
Um, let's see. So maybe we can kind of just talk about practical aspects of ETLFs. Do you think that they impact a landfill capacity or a landfill's ability to do business?
Yeah. Um, they might. I mean, I think we get into it's going to be site specific, right? But let's look at a couple hypotheticals. One is a landfill with no nearby neighbors, and they've gotten on top of it. They have good cover. They're collecting the gas. They're combusting that gas, so there's complete combustion and no odors. There's increased leachate generation, so they might have more trucks coming in to haul that leachate off. And if they're controlling odors, then there may not be any interference with doing business. However, if they may have to redo their fill plan. In other words, you may not want to put more waste on top of hot waste or more waste right adjacent to hot waste. So that could influence a fill plan, and that begs then, okay, well, what are the options? So if you have a site where that's the only place to put waste, yeah, it could influence it. If you have a site where we can say, hey, look, let's just fill on the other side of our permitted footprint for the next however many years and let it cool, then if odors are under control, it shouldn't impact business. Um, and the flip side of that is I've been at sites where the odor was not under control. The community was rightfully concerned. And one can imagine a regulatory agency suggesting that they need not be bringing in more waste, or they have to develop a new cell to develop waste. So there's lots of scenarios. Every site is specific. It can most definitely impact operations and cost.
Yeah, that makes sense. So kind of two questions here. One was a clarifying question on what an HOV is.
Higher operating value, I believe. So when your well go, the traditional regulation said that if your temperature in a gas well exceeded a certain number, and it used to be 131, I think it's increased now, and I apologize, I don't remember the new number. But if it increased above a certain number, the assumption was that you were drawing in air, the air was reacting with the biodegradable organic matter, and under aerobic conditions, that reaction generates considerable heat. So the assumption was you're drawing in air because you've got too much vacuum on your well, you need to turn your well off. And so the regulation said if the temperature is above some number, turn the well off. Um, if you are pulling in air, that's the right thing to do. If you're not pulling in air, then turning your well off just leads to more heat accumulation and more pressure accumulation. And it's the exact opposite of what you're trying to do to manage an ETLF.
So then, how important do you think it is to get an HOV to allow gas extraction, I guess, in
Oh,
the case of an ETLF?
it's 100% essential. And, I think one of the objectives of these sessions, I think, is to help educate a wide range of practitioners, owners, operators, regulators, et cetera, who might not have access to cutting edge research on a weekly basis. And So I just tried to emphasize that uh, if an HOV needs to be issued, then issuing it is critically important. And that doesn't mean issue it and then walk away from the site. It means issue it and keep monitoring and make sure that you're doing everything you can to control, including removing liquids, good covers so your gas collection efficiency is as high as it can be, making sure the methane content in your to your destruction device, flare or engine, is high enough to destroy completely oxidized methane and volatile organics. So it's not just trust us with an HOV, but give us the HOV and let's have a conversation about all the things we're doing and need to do to manage this site.
Do you know of any other, I mean, so this will be available, we're recording the session, so folks will be able to use this as a tool for education purposes. Do you know of anything else that will be available outside of kind of the peer-reviewed publications and EREF documents that people could use to educate regulators or others in the industry or
Yeah.
landfills that are dealing with these issues?
Well, at the risk of putting people on the spot, which is not my intention, uh, I find the Global Waste Management Symposium to be a really good source of current information. It's every other year. So we're looking, I think, at February 26th. And I've thought, I don't know if those sessions have been recorded, but I wonder if going forward there would be value in recording them for people that are unable to attend, and then maybe setting them up in a way that people can get listen for a fee and get PDHs. And that, again, that's just an idea I've had. And the other EREF has sponsored. This is, I think, the first virtual session like this, but there have been 2 summits on ETLFs over the years, and attend them. And I know that's easier said than done. I know particularly people in the public sector may struggle with travel budgets, but getting out and talking to people is really important. I would be pretty nervous if all people did was read, but I think the literature, it's there. I'll be the first to admit that it's written for academics and it's a bit dense. But we also have an EREF report on the model. So there's at least 3, plus Debbie Reinhardt's got one on ash. There's at least 4 or 5 EREF reports that are accessible to a broader audience.
Absolutely.
And Craig's probably got one as well. So yeah.
Yeah, so those are all available on EREF's website. If you're interested in downloading them, they are available for free. GWMS is a great event and a good opportunity for folks to learn about this issue and a number of different issues related to solid waste management. I think we're pretty much at time. So appreciate all of the wonderful questions that we got in. Apologies that we weren't able to answer them all. We'll see what we can do about getting answers to all of these questions. Please join me, I guess, in thanking Dr. Barlaz for his time. As I mentioned, this will be available. So I think with all of that, this concludes today's science session. Thank you again, Dr. Barlaz, for your time on this presentation and your expertise. Registration is now open for our next science session, Look Inside Methane Measurement at Landfills, a Controlled Release Study, and that'll be on December 4th. And then, as I said earlier, please look for an email tomorrow from Zoom with links for the presentation and a brief survey where you can download your certificate of attendance. We appreciate your feedback to help us improve these science sessions. Thank you so much for joining, and we hope to see you next time. Thanks, everyone.